Good afternoon, everyone. Am I audible to you all?
Yes, yes.
So, as we have discussed in the last class, the same way we will do in this class also. We will solve some problems. Thereafter, this time I have made a short video on transmission of data using LED and again the reception of data using photodetector. So this small experimental setup I have made in my lab. So I will show the video of that setup. And if you have any doubt, you can ask me in between. First, we will start some small questions. Then we will see the video. Thereafter, we will again will be doing our questions. If you have any doubt, you can ask me anytime in between. So this is the first question. The finite spectral width of the optical source causes. You have four options. It causes depletion, frequency burst, pulse broadening, or efficient reflection. If you know the answer, you can give the answer in the by putting your mic on, or you can write in the message box. This is a simple question. I hope everyone should know it. Yeah, correct. Anyone else? See, the spectral width of the optical sources. Whatever be your optical sources, either it be an LED or a laser, there will be some amount of spectral width. Let's say this is power, this is lambda. So this is your spectral width. This broadening for laser is very small, whereas this broadening for LED is large. So this is what pulse broadening. To send some pulse like 1, 0, there may be like broadening like this. Okay, I hope you have understand this question. Second question. In the population inversion, we have four options, 1, 2, 3, 4. The number of electrons in the higher state is more than the number of electrons in the ground state. The number of electrons in the lower state is more, or the number of electrons are same in both the higher and the lower state, or none of them. You have to give the one answer. You can write in the message box, or you can directly turn on your speaker and say the answer.
It's the first one. The number of electrons is higher in the higher energy state is more than ground state.
Yeah, correct. This one is the correct answer. Obviously, for laser, you need some population inversion, and there may be a 3-state system or 4-state system. So when electron goes from lower state to higher state, then it's come back to higher to, this is meta state, meta stable state. The number of electrons in these levels are very high. And then when they come to this metastable state, they all are in same phase. And this process of accumulating more electrons in the higher energy state is called pumping. It's called pumping. And this large number of electrons come into the lower or metastable state at the same phase, and they are like coherent system. So they make the light to be coherent. Whereas in LED, what it happens? The electrons goes from lower energy state and it comes to lower to higher and comes to higher to lower energy state spontaneously. Whereas in laser, we have 3 or 4 states, and optical pumping is there by supplying an electrical energy through the device, supplying energy to the device. This is what called as pumping. So through pumping, the electrons goes from lower energy state to higher energy state, and then they all comes to the metastable state and they remain in same phase. So this makes the laser a coherent system, whereas this type of system is not in LED. So that's why it is spontaneous, whereas in laser it is stimulated emission. Next question, the condition needed for laser action is
stimulated emission.
There may be a multiple correct answer, so please.
Stimulated emission population inversion.
Okay, correct. These are the simple question. I think everyone should answer it.
Coherent.
Yeah, coherent. And like this is a multiple correct answer. So like the answer is only coherent, or you seems can you answer multiple? Can you see a multiple correct answer here?
That's monochromatic.
Coherent one is correct. Other than this,
Monochromatic.
monochromatic.
Highly intense also.
Yeah, highly intense is also correct, because intensity is like power per unit area. So that if you see about the coherence are of two types, like temporal coherence and second is partial coherence. So spatial coherence means it is coherent in the space domain. So one thing you can see in laser and LED. So this is LED and this is laser. Laser are highly coherent in space. They are like unidirectional and they emit only one wavelength kind of thing. So whereas for LED, they emit light in all the directions. They emit light in all the directions. So they are not like coherent in the spatial domain, whereas lasers are coherent in the spatial domain. And this, because of this coherency, the intensity at any instance is very high. Density power per unit. Here power is distributed in the complete area, where here power is confined in one direction. So the intensity is very high for the laser. That's why whenever you want to send data using LED or laser, LED are used generally for small distance, whereas lasers are generally used to send a data to a long distance. See, you have heard about Wi-Fi. What Wi-Fi do? Create a internet kind of thing in a local area where transmission of data can be happen. So same thing you can do with light also. Light like LED or lasers. So in a room, in particular room, using LED, we can create a Li-Fi kind of thing. This using, if we are doing this with a light, then it is called light fidelity. So using LED, we can create an Wi-Fi, like Wi-Fi kind of thing, which is known as Li-Fi. And this is in coming time, this is very important. Why it is important? Because light has, you all know that light has higher bandwidth, higher capacity, and speed from our data rate. So these are the benefits of light. So in coming times, in place of Wi-Fi, Li-Fi can be used. And one more advantage of the Li-Fi is security. See, light cannot penetrate the wall. So if you are conducting some meeting in a particular room, then your data will remain in that room only. It will not go outside the room. Whereas Wi-Fi can go outside the room. So these are the advantage of Li-Fi over Wi-Fi. So and also other than that, these are also the advantage of the Li-Fi. So in coming times where data will be very high, that time you may require Li-Fi in place of Wi-Fi. And similarly, to transmit the same signal to a longer distance, we can use laser. So I think I have made the points clear how it is intense and what are the major differences between LED and the lasers. Next question. This is the last question. After that, we will see a video. Then we will start. After the video, we will start some numerical type of question. So keep a calculator with yourself. You need to calculate some numerical answers. In a photodiode, when there is no incident light, the reverse current is almost negligible, and it is called as. Again, you have 4 options. You need to give the answer.
Dark current.
Yeah, dark current is the correct answer. Obviously, this is like photodiode TN. This works in the reverse bias. See, photodiode or whatever the diodes that are used for the reception partner, like PN or PIN or avalanche photodiode, general photodiode, all these are used in reverse bias. And whatever the sources are used as a source, like LED, lasers, this all are used in forward bias. So this will be like reverse bias. Whenever the light falls here in the form of photons, electron hole pairs are generated inside the material, and this electron and hole pairs flow inside this material, inside the circuits, and we get a voltage at the output. So this is what the short working of an photodiodes. Now next I will play a video here. In that video, a simple square wave is generated using the function generator, and that this square wave or a pulse signal is transmitted through LED to optical fiber to the receiver it is received by photodetector, and then again we are seeing the signal at oscilloscope. So what will happen at higher frequencies, how the signal is transferred through whole the medium, that you can see here. So let me play this video. Here you will use optical fiber to transmit a signal from one place to another. In our lab, we have used 5 meters of optical fiber, but in practical, we can use thousands of kilometers of optical fiber and transmit a signal from one place to another. First of all, we have used function generator to generate a signal. We have generated a high-low type of electrical signal, and now this electric signal will be fed to an LED, which will convert this electrical signal into light signal. And now this light signal will travel through the optical fiber from transmitter to detector. This is a photodetector. This detector will convert again the light signal into electrical signal, and we can see this electrical signal in CRO. So what we have sent at the transmitter, high-low type of signal, we can again receive the same signal at the receiver. Nowadays, companies like Google send their signal from one country to another using optical fiber. As optical fiber can have data rate in terahertz, very low losses, highly secure, and send a signal up to speed of light. We will give 1 kilohertz of signal, which means that LED will be turned on and off 1000 times in a second. In our house, the light comes at an optical. Is it visible and audible to you?
Yes, yes.
Okay, thank you. Fiber can have data rate in terahertz, very low losses, high, again receive the same signal at the receiver. Nowadays, companies like Google send their signal from one country to another using optical fiber. As optical fiber can have data rate in terahertz, very low losses, highly secure, and send a signal up to speed of light. We will give 1 kilohertz of signal, which means that LED will be turned on and off 1000 times in a second. In our house, the light comes at a frequency of 50 hertz, but our eyes are not that much sensitive, so it cannot see the blink of light. The same happens here in LED. We see a continuous intensity of light. Now we will see the output in CRO. For this, we have to set the time scale from seconds to milliseconds. We can see a little bit of disturbance here. To understand this more clearly, let's set the input frequency at 10 kilohertz. Now, again setting the time scale, we can see a change in shape at output. This shape change occurs at 10 kilohertz due to the limitation of photodiode. Let's understand this in more detail. As we are giving a rectangular pulse at the input, we should also obtain a rectangular pulse at the output if the width of the depletion is large and capacitance is small. But if the capacitance is large, then the RC time constant will also be large, and this large RC time constant will lead to slow convergence at the output. As in our experiment, the value of RC is fixed. So if we increase the frequency beyond 10 kilohertz, then there will be a distortion in the rise time and the falling time at the output. And this is the reason why we see a shape change at the output. Now let's move ahead and set the input as sine wave of 1 Hz. Now we can see at the output for the positive half cycle we receive the same signal as input, but for the negative half cycle it is zero. That because LED is a diode which works in forward bias, and for the reverse bias it is turned off. To see the complete signal, I am giving an offset of 3 volt at the input, which will make our signal from -2 to 2 volt to 1 to 5 volt. So here we can see that the intensity of the LED is varying as a sine wave, and the same we can see at the output of the CRO, a full sine wave. Now, lastly, we will understand the connection of photodiode and end up our video. Here, this is the pin diagram of photodiode. Here, pin number 1 is connected to power supply of 10.6 volt, but we can connect. Uh, so this was the video. I hope you all have enjoyed it. Um, Here we have shown the transmission of light or data. We have a pulse kind of signal to the receiver side, and this was the small setup and demonstration type. Anyone have any doubts regarding this video and thing? Or do anyone want to say anything about this? Ramdeep, Ramandeep, sorry.
No, it's okay. It was good.
Okay, so okay, so let's move to the next section.
Sir, is it a multi-mode or single mode fiber?
This was a multi-mode fiber. The matlab, it's like generally the multi-mode fiber are made up of like glass, but this wasn't this multi-mode fiber was a little made up of plastic, and this was an like the higher order of multi-mode fiber, uh, like core diameter of around 200 micrometers. But generally a multi-mode fiber have a like core diameter of 50 micrometers, but I kept this kind of multi-mode fiber because if I keep a multi-mode fiber of like 50 micrometers, then the coupling of light will be very difficult. Then we have, if we want to couple a light from LED to a fiber, then we have to make some arrangement of optical lenses to converge the light and all that. So I was willing to make a simple setup. That's why I have kept a multi-mode fiber of like this kind of higher order and of higher core diameter. The core diameter was around 200 micrometer for this. So, and also it have an acceptance angle of like 50, 45 degree and numerical aperture of 0.5. So this is about the multi-mode fiber that was used here. Anything else? Okay. So now we will be solving some numericals here. So I will show you the numericals, and I am expecting that first you will try to solve it. And if you get the answer, you reply me. And once some of you get the answer, then I will solve the answer. So this is the first question. A ruby laser contain a crystal of length 4 centimeter with a refractive index of 1.78. The peak emission wavelength from device is 0.55 nanometer. Now you have to determine the number of longitudinal modes and their frequency separation. You first try it yourself, then I will give up the answer. If anyone of you have got the answer, you can write in the message box. Do anyone of you know what are the longitudinal modes in a laser? What do you mean by modes in a laser? See, what happens in laser? This is suppose a cavity. The cavity length is L. So the electrons oscillate in between. And if suppose these are of mirrors M1, M2. So when an electron oscillates between these mirrors, this this is like pure reflecting, 100% reflecting, and this is like 95% of reflecting nature. So when electron is emitted out of this source, then they are like coherent. Then and further, when there is a generation of light, so this can generate only integer number of frequencies or wavelength. This generate some integer number of frequency or wavelength which satisfy the condition of gain. I hope if you saw the videos of the Anand Srivastava sir, then here we have seen that if you satisfy the gain and phase conditions, then only this will come out. So only integer number or some number of lights can only come out of the lasers. So these are known as modes. So these are known as modes. So ideally there should be only one mode. One mode should come out of the laser. But practically making a single mode out of the laser is not possible. So multiple number of modes are coming out of the laser. So these are the modes of the laser. So to calculate the modes of the laser, formula is like M equal to, derivation of this formula have been done by done in the NPTEL's video. That's why I'm not taking on the derivations here. 2NL by lambda, where N is the refractive index, L is the length of the cavity, and wavelength is their wavelength. So wavelength is given here 0.55, length is 4 centimeter, and refractive index is 1.78. If you put all this value here, then you will get the number of modes. Anyone if you have got the number of modes? Two into N is 1.78 into L 4 centimeter, or if I write it as meter, 10 is to power minus 2 upon lambda 0.55 nanometer, 10 is to power minus 9. If anyone, if you have got the answer, can write it in the message box. See, every time, every Saturday we'll be having this class from 3 to 5, and every time the process will be like this. I will set up some video and show you some video, or I can show you in real time also, and that depends. And we'll solve some simple questions, and after that we'll solve some pure numerical type of questions. So I'm hoping that you will be trying by yourself. If you put all this value, you will get approximately 2.6 into 10 raised to power 5 number of modes. So this is the 2.6 into 10 raised to power 5. So this is the number of modes you will be getting. The next part of this question is, what is the frequency separation? So if this is like frequency axis, then what is the separation between these two modes? If it be a like wavelength axis, lambda, it will be like the separation between these two modes, any two modes, is delta lambda. So here frequency separation, then it will be delta f. So delta f is c upon 2n L, where c is velocity of light, n is refractive index, and L is the length of the laser. You put the value of C, N, and L, you will get the answer.
For M, it is coming 2.6 into 10 to power 7, I think.
Okay.
10 to power 10 to power 5.
Okay. Maybe. Maybe I have made some calculation mistakes. I will check it. It may be like 2.6 into 10 to the power 7. Okay. Thank you. Next part, delta F, 3 into 10 to the power 8, 2 into 1.78 into L, which is 4. If you solve this, you will get the delta F to be, anyone have solved this answer? 1.4 gigahertz. So again, I am getting 2.1 gigahertz. Okay, I will check the numerical part, calculation part. There may be some mistakes. Delta F. Um, but the theory and the values are same only. So I will check the, or anyone else have got the answer? Then it will be verified that it is 1.4 or 2.1 gigahertz. And one more thing you can see here that M is number of modes and it is equal to 2NL by lambda. M equal to, yeah, Omul Ghani, yeah, 2.1. I am also getting 2.1. So, Ramandeep, you need to check your answer. So, M equal to 2NL by lambda. So, ideally you should get M as in 1, means only one single mode. So, if you put M equal to 1, then 2NL by lambda, and this L will be lambda by 2n. So here you can see that the length of the cavity should be in the order of lambda. Means if n is air, then L should be lambda by 2. So making such small cavity of the orders of wavelength. See, wavelength, you know, that is in like nanometers or picometer, and making such small cavities with such precision is very difficult. That's why it is said that single mode lasers are very difficult to manufacture and to obtain. So whenever you will see that any laser is emitting any single wavelength, that means that laser will be very highly costly, and it will be very costly because making this length with so much precision is very difficult. I hope you have got this point. Let's move to the next question. Next question is more of the similar type of question. First, you need to calculate the number of modes, and second, you have to calculate the separation, delta lambda. So you try it yourself, then I will give the answer. How many half wavelengths span the region between the Fabry-Perret mirror surface? Consider a double heterostructure as emitting Fabry-Perret aluminum gas laser which emits at 90 nanometers, no, sorry, 900 nanometers. Suppose the laser chip is 300 micrometer long and the refractive index of the laser is 4.3. So you need to calculate how many wavelength, that is basically the number of modes, and suppose second, what is the spacing between the lasing modes, which is delta lambda. So first we have to calculate number of modes and second delta lambda. So we know that number of modes is 2NL by lambda. So if you put all these values, you will get the answer as 2 into L is 4.3. Sorry, N is 4.3, L is 300 into 10 to the power minus 6 upon lambda, which is 900 nanometer, or you can write it as 0.9 into 10 raised to power minus 6. To solve this, you will get, anyone have got the answer?
2.8 into 10 to power 3.
Yeah, correct answer. This answer was given by
Yeah, Ramandeep.
Ramandeep. Yeah, correct answer. Good. So you will get somewhere around 2866 number of modes. Next, delta lambda. The formula for the delta lambda is lambda square upon 2NL. If you put the value of this, you will get the answer. The question in your assignments are similar to the questions that we are solving here. So if you solve this question, if you be familiar with this question, you will be able to solve the assignments questions that are given in the week 2 of this series. (900 into 10 to the power minus 9 whole square upon 2 into 4.3 into L, which is 300 micrometers. That means 10 raised to the power minus 6. So the answer is 0.314 nanometer. So this is the answer. I hope you all are getting this answer. 0.314
Yes, sir.
nanometer. Yeah, good. Let's move to the next question. Next question is, an injection laser has an active cavity with a loss of 30 centimeter inverse, and the reflectivity of each cleaved laser is 30%. Determine the laser gain coefficient for the cavity when it has a length of 600 nanometers. So alpha is given here 30 centimeter inverse, and you know the formula of gain. You need to find the gain coefficient. You know the formula of gain, that is alpha plus 1 by L or 1 by 2L ln 1 by R1 into 1 by R2. Here it is given that the reflectivity of each cleaved laser is 30%. Means R1 is equal to R2 is equal to 30%, 0.3 or 0.3. Yeah. Now you can write this formula as like this also: alpha plus 1 by L, because R1 into R2 is R square. The square will come in front and it will 2 cancel out. Ln 1 by R. You put the value 30 plus L 600 nanometers. In centimeter, it will be like 600 into 10 raised to power minus 7 ln 1 by 0.3. If you solve this answer, if you solve this, you will get the answer. Do anyone if you get the answer? So the answer that I am getting is 50 centimeter inverse. So this is the gain or GTH. I hope you are getting the answer. Let's move to the next problem. This question is related to the photodiode. The question is, when 3 into 10 to the power 11 photons, each with a wavelength of 0.85 nanometers, are incident on a photodiode on an average 1.2 into 10 to the power 11 electrons are collected at the terminal of the device. Determine the quantum efficiency and responsivity of the photodiode at this much nanometers. So first thing, you need to determine the quantum efficiency. So what will be the quantum efficiency for a photodiode? Can anyone tell the answer? What is the quantum efficiency for a photodiode?
Number of electrons generated by number of incident photons.
Yeah, correct. In case of photodiodes, it is like number of electrons that are generated or that are present in the device due to the upon number of photons that are incident. But in case of sources like LED and the laser, the quantum efficiency is just opposite to it. It is like number of photons that are generated divided by number of electrons out here. But when we talk about the uh, photodiode, it is just reverse of the what we have seen in the laser and the LEDs. So here will be number of electrons or number of electron hole pair, both are the same thing. Number of electrons or number of electrons hole pair upon number of incident photon. So number of electrons, you can see here on an average of, we are getting this much of electrons, 1.2 into 10 raised to power 11 upon number of incident photon. So you can see here, number of incident photon is 3 into 10 raised to power 11. So the efficiency that you are getting is
40%.
40%. Correct. Got it? Obviously, in this is 0.4 or 40% efficiency you are getting. So next part of the question is, you need to calculate the responsivity of the photodiode at 0.85 nanometers. Responsivity, which is I upon P, or which is here efficiency into E into lambda upon Hc. Or if you put the value of H, which is a constant, C, which is also a constant, and E, which is a constant 1.6 into 10 to minus 19. This is 6.6 to 6 into 10 to minus 34, and this is 3 into 10 to power 8 meter per second. If you put all the value of this constant, you will get somewhere beta lambda upon 1.24. But this lambda will be in micrometers. Beta we have already got 0.4. Ramandeep have given the answer. Yeah, Ramandeep, your answer is correct. Into wavelength lambda. Zero point 0.85 into 10 raised to power minus 3 upon 1.24. So this you will get 0.27 4. So 0.274. This answer. Let's move to the next question. This will be last question for today's session. Photodiode has a quantum efficiency of 65%. When photons of energy this much are incident upon it, at what wavelength is the photodiode operating? First part. And second part, calculate the incident optical power required to obtain a photocurrent of 2.5 microampere when photodiode is operating at as described above. So you know that at what wavelength lambda is hc by E. If you put all the values, it's like 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by E, which is 1.5 into 10 to the power minus 19. Sorry, just a minute. And 5 into 10 to the power minus 19, which is given here. If we solve this, we'll get a wavelength as 132. It's like megahertz. See, it is wavelength. How it can be in megahertz? Please check your answer. This wavelength. We will get wavelength as 1.32 micrometers. So next part of the question, you need to calculate the incident power required to obtain a photocurrent of this ampere when the photodiode is operating as described below. Part A, part B. Can anyone give me some idea how to solve this part B of the question? How to solve this question? Any idea about this? See, we know that R is equal to responsivity is equal to I upon P. The output current and incident power. So if we if we find the value of responsivity, we have the output current, we can find the power. So first we need to find the responsivity here. So R will be like theta E divided by HF. So if you put the value of theta E upon HF, you will get the answer. you will get the answer as 0.694 ampere watt inverse. So try it yourself. I am giving some time to you. Then we'll see the value of power. Do anyone have doubt in this part? How we have got the 0.694? See, Nita is 0.65 already given in the question. E is 1.6 into 10 raised to power minus 19. And we know that energy, which is equal to h mu, which is 1.5 into 10 raised to power minus 19. Put all this value, we will get this one. Now, here we do R0 I by P, and P incident is I by R. Put the value of I and R. I is 2.5 micro ampere, and R we got 0.0694. To solve this, we'll get the answer as 3.6 microwatt. So this is the power that need to be incident to get this much of current at the output. So this is it from my side. Any feedback from your side regarding the session we have conducted here? Okay, I'm ending the session. If you have any doubt, suggestion, you can say it here. So I will be keep adding up in the coming classes. Okay. So thank you everyone. Thank you for everyone for joining.
Thank you.